Hello, welcome back. This is Chris from Remote Energy, and in this short presentation, we're going to talk about the solar resource. We're going to discuss how we can quantify the amount of solar energy that reaches our sites. Let's get started. And here are the learning objectives for this presentation. When we're finished with our discussion today, you should be able to define what peak sun hours are. You should also be able to differentiate between the terms solar irradiance and solar insolation. One of the very important skills you should gain from this presentation is the ability to research and find out the monthly average peak sun hour value for your location. So you should be able to find a resource that can tell you how much sun is available at your specific site. And this is very important when we move on to talking about system sizing. And finally, by the end of the day here, you should be able to describe the impact of tilt angle on monthly and annual performance of a solar system. So how does changing the angle of the PV module affect its performance in a given day or a given month? All right, let's get into it. Before moving too far along in our discussion about the amount of sun that's available at any given spot on Earth, we need to draw the distinction between two terms. And these are two terms that we will use throughout this lesson, and they're terms that you're going to come across when you start researching the amount of available energy that's available from the sun in your site. The terms are solar irradiance and solar insolation. Now, although these are very similar, they're actually quite different. And I like to draw the distinction between the two, like we draw the distinction between the terms power and energy, because they're very similar here. Solar irradiance represents an instantaneous value. It's how much power is available at a given time of day from the sun. Typically, we use the unit watts per square meter to define solar irradiance. So a typical value, for example, might be 1,000 watts per square meter, and that would define how intense or how bright the sun is at any given time. 1,000 watts per square meter, by the way, is what we consider normal solar irradiance. It's what we might also call peak solar irradiance. And you might remember from earlier lessons that 1,000 watts per meter squared is a value that is used as a standard test condition when we're looking at PV module production. So solar radiance, again, is a instantaneous value. It represents power, and the unit that we use to quantify solar irradiance is the watt per meter squared. Solar insolation is slightly different. Solar insolation, like the term energy, includes a time component. So if we sum up all of the solar irradiance during the day, then we have solar insolation. How much power is available over the course of the daylight hours? And when we talk about time and power, now we're talking about energy. So solar insolation represents the amount of energy that's available during a given time period. Typically, the unit we use to describe solar insolation is the kilowatt hour per day per meter squared. And this is a very important term, solar insolation, that we will be using a lot when we start getting into sizing our PV array and calculating how much energy is available in a day from our PV array. Peak sun hours, or capital PSH as we abbreviate them, are a way for us to describe how much solar irradiation is available at a given location on a given day. This is important because we need to know how much sunlight is available if we're going to calculate how much energy we can produce from a solar panel that is at that location in a day. Later on, when we talk about system sizing, we're going to use peak sun hour values to calculate the amount of energy that our solar array will make. In this chart, we have solar irradiation in watts per meter squared on the vertical or the y-axis, ranging from 0 watts per meter squared all the way up to 1200 watts per meter squared. And on the x-axis are all the hours of the day. So this chart is showing the solar irradiance values over the course of one full day. If we take a look at that orange line, that is depicting the intensity of the sun or the solar radiation during the day. And starting off in the morning hours, we can see that the sun is rising maybe here at about 4 or 4:30 in the morning. And as the sun increases in altitude, the intensity of the sunlight increases, the solar irradiance increases. And in this case, we're getting all the way up to maybe 1100 or 1150 watts per meter squared at solar noon. And solar noon is the apex of this curve. And the solar irradiation starts to decrease then in the afternoon all the way back down to sunset. This curve is what we call a bell curve because it is, well, it kind of looks like the shape of a bell, and it's very typical of a solar irradiance curve. Anywhere on Earth, this is the shape of the solar irradiance if we look at it graphically. If we look at it mathematically, we can say that all of the area under this curve is the amount of total solar irradiation that's available on that day. So if we were to add up all of the area under the curve, we would have a value of the amount of solar irradiation. The big challenge here is we need to figure out a way how we're going to add up that area under the curve. It's not an easy shape to find the area of. So in order to do so, we need to think about it a little bit differently. And the way we do this is we take all the varying irradiance throughout the day, a little bit in the morning and the evening, a lot in the midday, and what we do is we take all that and we turn it into a value that represents the available solar resource as if the sun was at its peak for a specific number of hours instead. When I say peak, I am referring to 1,000 watts per meter squared. This value is what we call the peak sun value. And hopefully you remember from earlier lessons that 1,000 watts per meter squared is also the value that's used as a standard test condition for testing PV modules. So that's like a bright peak sun, 1,000 watts per meter squared. So what we're going to do is we are going to change the shape of this curve and figure out how many equivalent hours of peak sun we have instead of all these hours where there's a little bit less or a little bit more than 1,000 watts per meter squared peak sun. So we're taking the area under the bell curve and turning it into a rectangle instead of a curve. And this rectangle has a height at 1,000 watts per meter squared. This is, again, the peak sun, the peak intensity, and we're going to figure out how much of this bell curve will fit into a rectangle that has a value of 1,000 watts per meter squared. Now, when we do this, the area is the same. The area that we had under the bell curve is the same as the area we just created under this rectangle. So now 1 peak sun hour is equivalent to 1 hour at 1,000 watts per meter squared. So these dotted lines here signify 1 hour. If we take all this area under the curve, we turn it into a rectangle, and we look at that rectangle and see how many hours of peak sun we have. we can add up all those hours, and we have, in this case, a total of 6.5 peak sun hours. So a peak sun hour then is equivalent measure of the total solar insolation in a day given in kilowatt hours per meter squared per day. So this is a really important way to look at sun during a day. We've taken this variable irradiance all throughout the day and we've turned it into one number now, a peak sun hour. And we can use that number when we move forward with our calculations. Instead of saying that we have variable light all day, we can say, oh no, we have the equivalent of 6.5 peak sun hours in one day of irradiance at this site. That's what we'll use. Now, a lot of people, you might ask them, how much sun do you get at your site? And they'll say, oh, it gets light out at 6 a.m., it gets dark out at 6 p.m. We have 12 hours of sunlight. And they'll make the mistake of using that number for their calculations. But really, those are daylight hours. Those are not peak sun hours. Very important difference there. We're looking at the equivalent of how many hours of peak sun, hours of 1,000 watts per meter squared do we have if we add up all of the sun that's available in one day. So this peak sun hour value is something that we can research. We can find this value for given sites. It's important to understand that weather might affect this value. So if it's very, very rainy, this peak sun hour value might be less. So important to understand some of the factors that come into calculating this peak sun hour value. We'll talk more about this value and finding these values here a little bit later on. As we'll see, there's many different sources for finding peak sun hour data for specific locations. This is one way by using a world insolation map. This might not be the most accurate way to determine solar insolation for a given period, but it's an interesting way to look at it, to get a kind of a bird's eye view of where on Earth you have areas of really high intense sunlight and higher insolation values. So you could take a look at this chart and figure out where you are on it and get a rough idea of the yearly average solar insolation in kilowatt hours per meter squared. One of the interesting things here is to note that the equator, which actually passes about right here, is not the spot on Earth where we have the highest amount of annual solar insolation. The highest amount are actually about 25 or 30 degrees north and 25 or 30 degrees south latitude, so south and north of the equator. And these are the spots on Earth also where we have the big arid regions, the big deserts on Earth. We have the Sahara Desert here, the Kalahari in southern Africa, at about the same latitude in South America as the Atacama Desert. Much of Australia here falls into that category. And then when we look at the very high latitudes, we see much less solar insolation. And this is because the sun's rays actually hit the Earth's surface at a different, lower, less direct angle at these higher latitudes. And this actually spreads the same amount of solar energy out over a larger area, which results in less insolation on the Earth's surface. So very interesting way to look at world insolation. Not a great way to come up with values to use in calculations. We'll look at other sources here in a minute. Just wanted to include a close-up here of that global insolation map. And just look at Africa for a second. This is a peak sun hour map for Africa. And if you look carefully at this map, you'll see that inside the colored regions are numeric values. I'm looking at Algeria and I see 5.8, I see 5.5 over there in Libya. In the darker, the orangish, reddish color is, the higher the peak sun hour value is in this map. Keep in mind that a peak sun hour is equivalent to 1 kilowatt hour per meter squared. So when we see these maps, sometimes uh, the map will say that we're looking at kilowatt hours per meter squared. Sometimes they'll say we're looking at peak sun hours. They're the same thing. We just need to remember that 1 peak sun hour is equivalent to 1 kilowatt hour per meter squared per day. Again, these maps aren't the best way to find information. They're a nice way to get an overall picture, a basic idea of where the sunlight might be the most intense in a region. But to really find values that we need to use in the calculations, we have to dig a little bit deeper into some resources. And here are a list of online sources for solar insolation values. So as I mentioned, the maps that we looked at provide a nice overview and a basic big picture of what peak sun hours may be in a region. But really when we're getting into sizing PV systems for specific locations, we need to have a little bit more detail, a little bit more granularity in our data. So we're providing you here with 4 different sources. These are online sources where you can find peak sun hour data or solar insolation data. Very important, and you'll see this in the coming example, that you look at multiple sources when you're exploring and researching your data. Sometimes sources will make assumptions about certain conditions that might affect the data that they're displaying. So you need to know exactly what you're looking at. You need to compare apples to apples, as we say, to make sure that the data you're looking at is the most relevant for what you're trying to learn. The first site on here, the Global Solar Atlas, this is a fantastic resource. Highly recommended that you spend some time, follow this link, and explore a little bit. Lots of great resources here. There's maps, there's tables, there's graphs, all kinds of information about the solar resource in sites all over the world. PV Watts is another great resource. This is provided by the National Renewable Energy Lab in the United States. You can follow that link there and they can walk you through the insolation data. FretScreen is another one, a great program. And I also want to bring your attention there to GASMA, GASMA.com. This is a resource that pulls data from the US government database, but it does have data, some of which is measured, some of which is modeled data. So it's not actually data that people have measured, it's data that people have projected from satellite imagery or other data modeling software. But it's a very easy resource to use, and it does provide a lot of really interesting information. So take some time and explore these resources, find the data, compare the data, make sure it's data that is relevant to what you're doing, and then decide which of the resources is best for you. This is what the data looks like when you go and explore these online resources. Typically, you will receive peak sun hour data or solar insolation data in the form of kilowatt hour per meter squared per day for every month. So we're receiving the monthly average peak sun hour data. This particular example is for Dakar, Senegal. So we typed Dakar, Senegal into the online databases, and this is the peak sun hour or solar insolation data that they've given us. In the first example, we used PV Watts, which was one of our resources on the previous slide. And when we typed Dakar, Senegal into PV Watts, this was the data they provided. And PV Watts actually provided us with 2 different data sets. The first data set, which is the darker orange line with all the numbers in it there, those are the peak sun hours that are measured if we are measuring them from a tilted surface. So we're actually looking at a collector. We could say that, oh, if this was a PV module, it would be tilted up at the angle of the latitude of the site. So the Car Senegal has a latitude of 15 degrees. In this case, we are measuring the solar irradiance from a collector that is angled at 15 degrees. Essentially, we are collecting that solar irradiance at a right angle, which would give us a higher value than if we collected it from a horizontal or a flat angle. And that's very important to understand. We need to know when we're looking at this data, if we're looking at horizontal data, if we're looking at data that's collected using the latitude of the site, or maybe, as in the next example, we're looking at data that's collected at the latitude angle plus 15 degrees. So this is actually data that's collected from a collector that's angled up 30 degrees from horizontal. And you'll see that this angle actually does affect the amount of insolation annually or monthly in that site. So looking at the latitude angle insolation, that first column there, we can see that in the month of January, a solar panel, for example, that's tilted at the latitude angle of 15 degrees will receive 5.45 peak sun hours, or 5.45 kilowatt hours per meter squared per day of solar insolation. Now, if we were to tip that solar panel up 15 degrees more to 30 degrees at the same site in the same month there, January, we would actually have 5.8 peak sun hours measured, or 5.8 kilowatt hours per meter squared per day. That's a slightly higher value. And what is that telling us? Well, that probably means that the sun is at a lower angle in the month of January. And therefore, by tilting up the collector to 30 degrees instead of 15 degrees, we're allowing the sun's rays to hit the collector at a more direct angle, closer to a right angle, and we're actually receiving more solar insolation on that surface. So two very different values there for the same month at the same location. Again, the values are different because we're using a different angle to collect that solar insolation. Looking on in that same data set, if we move to the months of June and July, you can see that the collector that was angled at the latitude angle of 15 degrees is actually receiving much higher insolation values in the months of June and July than the one that's tilted farther up. And this is because now that the sun is at a higher angle in those months, and the collector that is at a lower angle is actually now receiving more direct solar radiation. The very last column there in this first data set shows the annual average. So in this particular site, if we had a collector that was angled at the latitude angle, we would have an annual average of 5.73 peak sun hours per day. And if, again, we tilted that collector up 15 degrees, so we had a collector that was actually now at the latitude angle 15 degrees plus 15 degrees, so a 30-degree tilt, we would receive 5.56 peak sun hours, or 5.56 kilowatt hours per meter squared per day. So that tells us that a PV module mounted at an angle of 15 degrees, the latitude angle of the Car Senegal, would have an annual average a higher peak sun hour annual average than one that was tipped up at a slightly higher angle. Now, don't be too concerned about all these numbers right now. The idea here is just to understand that there are varying data sets, and they're varying typically on how they collect the data, what angle they're using to collect the data. And you can see now, if we go down to the next one, the GASMA values, these are much lower looking values than we're seeing in the chart above. For example, in the month of January, the GASMA data set says that there's 4.87 peak sun hours in the month of January instead of 5.45 or 5.8 from the PV watts. Now, there's not a whole lot of information on here about what that GASMA data came from, but it's probably using a flat surface there instead of a tilted surface. So this GASMA data most likely is using a horizontal surface. And that's great as long as we know that that's what we're looking at. So at a horizontal or a flat surface in that same site, it looks like we have much higher solar irradiance in the May, June, July months, and then much lower in the January, February, and the November, December months. So interesting here that, again, we have two very different data sets that are giving us different numbers, but they're different because in how they measured the data. That global solar atlas data set, the third one there at the bottom, is also giving us monthly average values. And you can see that these are also different yet. Turns out that the global solar atlas data here is not giving us solar insolation values at all. What they're actually giving us is they're telling us how many kilowatt hours could be produced by a 1 kilowatt PV array. So it's a slightly different data set altogether. This is looking more at energy production instead of solar insolation. So again, just showing different ways here that data is presented. Very important to understand what you're looking at. The idea here is not to worry about which one should I choose, what should I do, but just to be aware that there is lots of different values out there. In future lessons, when we talk about system sizing, we will talk a lot more about which of these values we should be using to determine how much energy our PV array is going to make. So take some time, explore these sites. I think you'll find it very interesting to learn a little bit about how much sun and how much energy is available from the sun where you live. And it's been a pleasure. We will talk a lot more about this in future lessons. I hope you enjoyed the presentation. Thank you.